that will talk about the Dune experiment. Hi, Ettore.
Hi, John. Can you hear me?
Yeah.
Okay. I'll share my screen. Can you see my slides too?
Yes.
Okay. First of all, thank you for the invitation. It's always very exciting speaking at SILAFAE. I will give you an overview status of the Dune experiment. I will talk a little bit of the physics goals, where we stand with the far side, with the far detector, with the near detector, and so on. We'll put some emphasis on the photon detection system, which is the area of the experiment where Latin America collaborators have the most relevant, most visible role, let's say, at this moment. Dune is ramping up. It's a global collaboration. We touched around 1,400 collaborators now from more than 200 institutions, 33 countries plus CERN. Here you can see the map in orange of the countries committed with Dune. You see also good participation from Latin America. Dune will give contribution, hopefully significant contribution to neutrino physics, and in particular to neutrino oscillation. The detector will have a significant sensitivity to measure the CP violation, symmetry violation in the leptonic sector, sorry, the neutrino mass hierarchy, and to perform precision measurement of the oscillation physics according to the flavor paradigm. We will be able also to perform the tile search for proton decay, which are decays which are foreseen by several beyond standard model theories, with a particular focus on the kind where the final status content counts. I will say something about this later. And we will be able to measure substantial amount of neutrino in case of supernova explosion in our galaxy or nearby galaxies, and perform also studies with the atmospheric and solar neutrino, even if this is not in the mainstream of the experiment. For what concerns the proton decay, Dune will be able to establish the mass orbiting of the neutrinos at 5 sigma level for about all the value of the CP violating phase delta CP in a time between 2 and 3 years. The CP violation, as you can see here in the plot, which is here on the bottom right, the CP violation could be observed with the significant of 5 sigma for value of delta CP in minus pi divided by 2 in about 7 years, and in 10 years for 50% of the delta CP values. To reach a sensitivity of 3 sigma, a significant 3 sigma for the 75% of the delta CP value, we need to wait 13 years. All this information is summarized in this plot in the top left. We will also have a significant sensitivity to the theta 2 octant for value sin square of theta 2 outside the interval between 0.47 and 0.555. Dune far detectors will be highly sensitive to several decay mode of the proton, in a way which is largely complementary to what can be done with large water detector. For example, grand unification theories have 2 benchmark decay mode, which is the proton going to the positron and to page 0, and proton going to a count and to a neutrino, which is the most favorable decay mode foreseen by supersymmetric model this first mode is very well measured with the water Cherenkov experiment, while the second one is better addressed by liquid argon detection. In fact, the count is typically below the Cherenkov threshold in water, while it is very easily identified in liquid argon to its feature in the this pattern of the X inside the liquid argon. Here you can see a simulated proton decay event with the count on the moon and producing a small electromagnetic shower in 3 different views, which we call induction 1 and induction 2 collection, which allow then 3-dimensional reconstruction of the event, complete 3-dimensional reconstruction. We'll say something later about this. And in case of no signal, we will reach a lower limit on the proton lifetimes in 10 years, at the level of 1.2 in 10 to the 34 years. In case of a supernova explosion, Dune will give significant contribution. Our fire detector are sensitive to neutrinos from about 5 MeV, where neutrino charge current interaction produce tracks with a length of few centimeters. Our resolution at the level of millimeters. The peculiarity of the Dune experimental techniques that we will be primarily sensitive to new interaction, to the absorption of neutrino electron on argon, which is unique among the existing proposed supernova experiments, which are typically sensitive to antineutrinos. This will allow to possibly observe the peak of the neutronization of the supernova, neutronization phase in the supernova explosion process. The supernova detection is a place where the photon detection system has a primary role. The sensitivity of our system, the efficiency, the detection efficiency of the photon detection was specifically designed to improve the performance of the detector at low energy. In fact, at low energy, as you can see from this plot, below, let's say 10 MeV, 10, 15 MeV, the energy resolution which we can get with the detection of photons is better than we can get with the detection of charge. This is a series of advantages which goes from the overall improvement of the energy resolution of the experiment, the better trigger scheme for supernova, reduction of the time, and eventually backupping the TPC in case of need. So there can be cases where the time projection chamber is not working because of failures of the voltage. In that case, the photon detection system could back up completely the TPC without losing an eventual supernova explosion. This is a sketch of the experiment, which is a complex experiment, which will be located at Fermilab. We will have high power wideband neutrino band with the peak around between 1 and 3 GeV, originating from Fermilab. The beam will be neutrino beam will be mounted by neutrino by near detector, which is located 500 meters from the origin of the neutrino beam, and then will propagate for 1,300 kilometers down to the surf underground facility in South Dakota, where a segmented 40 kiloton liquid argon fire detector will be installed at a depth of about 1 mile underground in a former gold mine. The beam is a very intense beam. It's the most intense neutrino beam ever built. Start with a proton beam at the level of 1.2 megawatt, which is measured again a target. Protons 120 GeV is measured again the target. The pions counts are then focused in the decay line. Pions decay into muon neutrinos, neutrino mu, neutrino tau, neutrino mu, antineutrino mu, depending on the selection of the polarity of the magnetic selectors, and then muon absorbed, the neutrinos are left to go toward South Dakota, and are monitored by the near detector facility. This is the beam which is expected at fire detector without oscillation. We see that the energy ranges from 0 to 10 GeV. Then there is a broad peak between 1 and 3, 4 GeV, both in neutrino and antineutrino mode. I will say something about the technology which is used in the fire detector, the technology with time projection chambers. The baseline detector is to deploy at the beginning two modules, each one with an active mass of about 10 kiloton. The models will be slightly different with a different configuration of the time projection chamber. Module 1, which is the one which will be deployed first, is a traditional temp chamber with the charge readout done with wires. There are 3 anodic planes, as you can see here, 2 cathodic planes, which segment the internal volume in 4 time projection chamber, each one with a maximum drift of 3.6 meters between the wire planes and the cathode plane. And the photon detector are based on X-ray technology, which are deployed inside the behind the wire planes. The model 2 has a slightly different technology, which is called a vertical drift, because the time projection chamber is rotated by 90 degrees. So there is a central cathode, the 2 anodic plane, which are made not of wires and the module 1, but made by PCB. The drift is 6.5 meters. So this allows for a better use of the internal space, so a larger active volume. In this case, the photon detection system is installed, is based again on X-ray technology. It's slightly different from this one, from the module 1. It's installed in the cathode. As you can see, these clear squares here represent the photon detection system, and on the walls of the crest. I will focus more on the module just as a simplification to module 1 photon detection system later. The techniques of the time projection chamber, probably very familiar to many of you, allows, as we say, to take electronic picture of the interaction of a neutrino. A huge liquid argon volume is immersed in a very uniform electric field, which is established between the cathode plane and an anode. The cathode is a normal plane, while the anode is made by parallel wire planes oriented in different directions. So when interaction happens, when a ionizing particle propagating the liquid argon produces a track of electrons and of ions, the ions goes undetected, while the electrons are drifted toward the wire planes, where are detected multiple times. The first 2 planes, in this case here we have 3 planes. The first 2 planes have the voltage such that they do not absorb the drifting charge. They only get induced signals, while the last plane collects the signals. So we call the first 2 plane induction, the third plane as collection. So the same track produces signals on the 3 different planes. Each plane gives a bidimensional representation of the event. And you can see here the combination of the 3-dimensional views give a complete 3-dimensional representation of any ionizing event inside the chamber. As I said before, this is a sort of electronic bubble chamber. This is a very beautiful example. This is a real event. It's a very microboom, which is an experimental experiment, as you probably know from the recent result about sterile neutrinos, which is the same experimental technique. This is a stopping muons, which is sampled with the wires which are a few millimeters one from the other. The spatial resolution is 1 millimeter. You can see that the muon loses energy. The NX is mapped with colors. So toward the back pricks, there is a huge increase of the energy deposition, and then you can see the Michel electron, which can produce the muon decay, which produces also a small electromagnetic shower with a few photons, which are also detected here. So there is a millimeter level space resolution, excellent energy resolution, beautiful capability of separating electron from gamma. We can identify particle through the NX versus the range. That is plotting the day over the X on each wires versus the range of the particle, for stopping particle, for example. And we have an excellent timing through the scintillation light. It's because we don't have only charge, which is produced by ionizing particle passing in liquid argon, but there is also a huge amount of scintillation light. In fact, half at the typical electric field which are applied in this in the TPC, which are at the level of 500 volts per centimeter, half of the energy goes into scintillation light. The production of the light is sketched in this graph. Both ionized argon and excited argon end up in the production, the formation of excited argon dimers, which we call excimers, which then decay to the fundamental state of two isolated argon atoms with the production of scintillation photons, which has an energy of 128 nanometers, which has energy 9.7 electron-volt and equivalent of 128 and 27 nanometers. So in the vacuum ultraviolet. And as I said, they constitute half of the, they represent half of the energy deposited by the interaction of liquid argon. Why detecting light is important, and how do we plan to use in Dune? First of all, we will use for the determination of the T0 for nuclear decay event, the nucleon decay events, because in this case, we don't have the timing of the beam. And so the T0 needs to be identified through scintillation light, which is a very fast signal, the level of a few nanoseconds, the tens of nanoseconds, which allow to fiducialize to identify the position of the event inside the TPC and to fiducialize very well the active volume and the discard efficiency of the background. The same will be done for supernova neutrino event. The scintillation signal will allow to localize each interaction inside the TPC and to correct for absorption of the electron during the drift. And then on top of this, the PDS will allow for complementary trigger schemes for the burst. This will increase the reliability of our trigger system combined with the charge, will reduce the time, and will allow the experiment to extend the sensitivity to nearby dwarf galaxies. And for all the neutrino interaction from the beam to neutrino, but also to proton decay, the PDS can be used to perform a calorimetric measurement and so improve the overall energy resolution of the experiment, exploiting the anti-correlation with the charge signal and eventually backupping the TPC when there is a failure of the high voltage system, for example. The photon detection system is the area where the Latin America contribution is very visible, and with leading roles for several reasons. First of all, because the system is based on the concept of the Rapuka, now in its last version, which is called the X-Rapuka, which is a concept developed by Professor Anna Machado and me, starting from 2015 at UNICAMP. As probably many of you know, the concept is based on the trapping of the photons inside the reflective cavity through the use of two wavelength shifters, one external to the cavity, just on the acceptance windows of the X-Rapuka, where the scintillation photons arrive. Photons are then allowed to enter the cavity, then wavelength shifting again, and the acceptance windows with the correct filter, which has a cutoff of 400 nanometers. So the second shifter shift the photons inside the cavity to 430, where the filter is reflective, and so the photons bunch inside the cavity and have an increased probability of hitting the active silicon sensor, silicon PM, which are installed along the sides of the box. Significant contribution are given in the area of the warm electronics, which has been completely developed by Latin American institution in collaboration with Fermilab institution, mainly from Colombia, but also with contribution from Paraguay, substantial contribution from Paraguay and Peru. On top of it, we grew in the last few years several groups which now have leading roles in the field of simulation and physical analysis involving PDS in general. So I believe this is we are proud of what we achieved up to now in the photon detection system in all this field. For the module 1, the photon detection system will be very similar to what was tested in product 1 up to 2019. This is the module in form of bars, which are installed behind the wires, which are dimensioned the wires of the anode plane assembly. Each the far detector 1 horizontal tip will have 150 of these. Each anode plane assembly will lost 10 photon detection module, extra Puka modules. So we will have 1,500 of these modules standard with far detector 1. And with the number of silicon PM, which exceeds 50,000. I will say something about Dune and the test which is coming just in a few slides. This is the far side, it's a sample on the underground research facility, which has 2 experimental sites at a depth of about 1,500 meters. The excavation started in 2017. This is a sketch of the site. There is the Davis campus, which also dark matter and double beta neutrino double beta decay experiment, and the Ross campus, which will be which is being largely increased towards the Dune experiment. So there are 2 shafts, Yates shaft and Ross shaft, which allows people to go down, people and material to go down. In green, you see the new excavation for the Dune experiment, which started in 2017. This is a beautiful landscape of the South Dakota of the experimental site. Here you can see the Davis site with the Yates complex and the Ross complex with the shaft down to the Dune experimental site. This is how the cavern will look like, 2 big caverns, which we lost the 4 far detector modules. Here is represented just the first one, and the central cavern where the facility for cryogenics and other things will be hosted. The status of the far side, the pre-excavation has been completed with all the equipment in place for the for moving the rock excavated from 1 mile underground to what we call the open cut, which is a place where all the rock excavator will go. This is shown here, and the construction of the Dune caverns is underway. Started just a few months ago in April 2021. Is expected to finish in April 2024. After which all the utilities for the underground will be installed. The heating, ventilation, air conditioning, of the electronics. Just after the completion of the 3 caverns. Here in satellite view of the site, it's the little shaft, and here is the trip that the rock take to reach the open cut. A very important achievement to be able to build the Dune far detector is the technology of the freestanding steel cryostat, which is motivated from the carriers of liquefied natural gas. This allows to build very big detector with the cost which is contained. This is a FD1, which will be a huge model with the length of 66 meters, which will be filled with about 1,000 trucks of 20 ton of liquid argon each. For what concerns the DIN and the near detector complex, the design of the beam line is almost finished, as well as of the near detector complex, which is shown here. It is the beautiful 3D representation on the beam line and of the near detector complex. The near detector is pretty is an integrated system with different detector. There is a highly segmented liquid argon temperature chambers with the limited drift length, which allows to follow the high flux of neutrino which we receive. This is called NDLR, which was followed by a multi-purpose detector, which is composed by a magnetized high-pressure gas argon TPC to monitor the muons, to have to study in more details interaction with neutrino in the gaseous phase, which makes some difference with liquid. There are some features which can be seen better, which will have also an electromagnetic calorimeter with the muon chamber and the superconducting magnet. These two detectors, NDLR and the multipurpose detector, have the ability of moving off axis for reasons that I will explain in a while. And then there is a beam monitor, which will sit always on axis, which is made by a magnet, which is refurbished by the experiment Chloe in Italy, and streamer tube tracker, and which will be installed in the center of the magnet. This will monitor the beam even when the NDLR and the multipurpose detector will be offline. This is a sketch of how it looks like with the liquid argon, with the NDLR in front of the beam, and the multipurpose detector, and then the Chloe magnet. The idea of the detector to monitor the beam, to constrain as much as possible the systematic of the experiment, to be able to make a clean measure at the far detector. As I said, the NDLR and the multipurpose detector can be moved off axis. This changes the spectrum, the energy spectrum of the detector neutrino, and this is very important because it will allow, with the sophisticated analysis techniques, to deconvolve the neutrino flux from interaction cross-section, and also to perform a mapping of the reconstructive versus true energy, versus the true energy response of the detector. So this is a very important feature which the detector will have. An important part, just to go to the last part of the talk, of the experimental program is the proto-Dune. The prototypes of Dune which are installed. We are showing the horizontal drift, which was formerly called a single phase, which have been operating up to beginning of 2020. And here is where we validated and demonstrated all technological choice, and we also perform some calibration using the charger particle beam delivered by CERN. Here, this neutrino platform at CERN, which is on surface. Here you can see the proto-Dune single phase with the horizontal drift. Here, where what was called the double phase was installed, which we lost in vertical drift, the proto-Dune vertical drift. Here's a very nice view of the internal of this of the cryostat of proto-Dune, which has the same technology which will be used for Dune. This is a really beautiful, really clean environment, and this before the installation of the TPC and the photon detection, all the internal system of the proto-Dune. Here you see the end of the installation with the white planes, with the photon detection, and with the cathode. Here you can see the representation of the international contribution to each component of the product. We spent there as a representative of the photon detection a good amount of time, was very experienced. And we will repeat it in the next year. I will encourage all of our Latin American collaborators to join us and spend some time at CERN helping with the proto-Dune data taking installation. These are some of the designs which were collected with the proto-Dune. This is a muon with the electromagnetic shower. This is a pion interaction with the four-pronged pion interaction. This is a very beautiful cosmic ray electromagnetic shower initiated by cosmic ray. And here you can see a three-dimensional reconstruction of one proto-Dune event. This is just one event. So these are all muons, the things which pass to the detector in the 3 milliseconds of the data acquisition for one trigger. And here you can see another view of another 3D view of one proto-Dune event. This is an atmospheric event. It is not no, this is a beam related. Here you can see the beam entrance. So this is the beam, the charger particle from the beam. Very important test. Proto-Dune was the for the photon detection system was the comparison of different photon detection technology. 3 different technologies we deployed together with the Arapuca. There was 2 different technologies which were compared. This is the final result, where each bar represented the photon collected by each module. This is our Arapuca, and this convinced the collaboration to choose this technology for the FAR detector. So this was extremely important for us. We are now preparing for Proto Dune Run 2. We are
3 minutes.
Yes, I finished. We are preparing for Proto Dune Run 2, which will happen in second half of 2022. We already are building component here in Brazil, particularly the mechanical part, the optics of the modules, while other components will come from Italy, other from Spain, and are for Colombia, and Paraguay, and Peru, in particular for the bomb electronics. Things are going through a pre-test process at CERN before being installed in Proto Dune, the Proto Dune I showed you before. This represents a very important test because it is the real module 0 of the FAR detector, because it will be the last test before the installation in South Dakota. In particular, for us, it's important because we will finally validate the Axel-Apocalypse design, and the Daphne board, as we call it, is the ground electronic for the photon detection system. So we are going to a very exciting phase. So we will get more data. We will be able to benchmark our detector for the operation on the far side. So this is my last slide. Thank you for your attention. This is our lab, and it's a place where the photon detection system of Dune, the far detector, will come together. It's the photon detection factor. Inside, we have all the facility to assemble and build all the models. Thank you.
Thank you, Ettore. Questions, please? Rogério?
Ettore, thank you very much for this talk. It's amazing to see all the effort and the collaboration in Latin America that goes into Dune. So I have 2 questions. One is, the Axel-Apocalypse will have to be, let's say, mass produced at some point. So where are you going to produce them? And the second question is the run 2 of the Proto Dune. First of all, what is the volume of Proto Dune? And then is it run only on cosmic rays, or you have real beams?
Yes, now we have a charger particle beam, so we will be able to detect particle from the beam with a well-defined energy range. There are protons, electrons, pions, and we don't have the restriction we had during run 1, because in run 1 we had a window of 1 month of data taken with the beam because of the long shutdown of the LHC. This time we don't have this constraint, so we will be able to take more data on the beam, which will be more easy. The volume is about between 700 and 800 tons of liquid argon. So it's huge. It's a cube of the internal dimension of the proton is a cube with the side of 6 meters. Is the biggest liquid argon. Is it a prototype? But in any case, the biggest liquid argon detector existing now.
Wow.
And the photon detection will be assembled here at UNICAMP, in the laboratory, the laptops. We will build most of the components in Brazil and São Paulo State. In particular, all the mechanics will be built by Equatorial in San Jose dos Campos, and the optics, that is the filters, will be built by the Opto company San Carlos. The coating with the shifter will be done here at UNICAMP, while the active photosensor are a responsibility of our Italian colleagues. So they will be built between Italy, and possibly we will buy a fraction of them in Japan from Hamamatsu. but everything will be shipped here. So the final assembly will be done here, and then from here we ship to South Dakota, when they will be stored and installed. It's a long process. Installation takes a couple of years. Will be installed in the far detector. But everything, I mean, the final component will come out from UNICAMP.
Fantastic. Thank you very much, and congratulations.
Thank you.
Ettore, how many collaborators from Latin America in the Arapuca project?
Yeah, I don't know exactly. I know that we have, there are 17 institutions, 17 from Latin America. All the consortium of the photon detection, which is behind the Arapuca, that is not only the Arapuca, the model, it is also the electronics on this thing, comprises 47 institutions. And there are 17 in Latin America, 15 or 16 in the US, and 16 or 17 in Europe. So it's very international. We started as a pretty Latin American effort, and then we were able to internationalize a lot, to attract a lot of interest, mainly from Europe, which are involved, but also on financial point of view. Half of the cost is shared with Europe, and I think it's the most international consortium of Dune. So it's, I believe is an excellent example for the collaboration in general. Yeah. Yeah. We started from scratch. We didn't have this lab. We reconstructed completely. And, I mean, I want to thank all the Latin American collaborators which are on board with us in this trip. Is very exciting.
And this Arapuca concept is being used in other kind of detectors, or could be used at least. Yes, I mean,
similar thing is used also in the near detector. In the near detector, the photon detection system is based on something similar. There are other efforts around which are inspired to this concept. What we are trying to do now is to develop an Arapuca which is sensitive to sharing of light, to use in water sharing of detector. This is Anna Melia is behind this, Professor Anderson Faut. They are putting forward this effort. We believe that is very promising technology, which could allow to use them instead of photomultipliers in the near future. We are pushing hard on this now.
Okay. Any other question? Rogério, are you seeing any hands?
No, I don't see any hands. So I can ask another question if no one wants to ask a question. So Ettore, I just didn't understand why the near detector has this superconducting magnetic field, and I think the far detector does not have one. Is that correct?
Yes, they are. Yes, there is the superconducting magnet to tag the muons, to have the precise tagging of the muon, to monitor the contamination of the beam, both in neutrino and antineutrino mode. So you can have a very precise monitoring of what is coming out from the beam.
Okay, so it's for measuring the let's say the energy of the muons. Okay.
Yes, and the sign, the polarity. Yeah, the far detector will be impossible because it's too big to put inside. It's really complicated. But for the far detector, which is smaller, so this is clearly possible.
Thank you, Ettore. I see a hand of Diego.
Yeah, Diego Rester.
Yes, I was wondering about the current schedule. When it is planned the experiment to start?
The current schedule, we are planning to start the installation of the modules just after the experimental hours are available, 2024, 2025. We should be able to install the first two modules by 2027, 2028, and the beam probably will not be available by the time, will be a bit later, but we plan to be running at least with Cosmic 2028. It's a very aggressive schedule because, as you see, they are building the underground facility now, and just after Proto Dune 2, we start the production of all the components. So we are quite optimistic about our schedule.
Okay, any other question?
Just a curiosity, is there enough liquid argon in the world for this?
Yes, is a good, I mean, is a sizable part of the world production, but yes, I mean, it is very, it is not cheap having all this liquid argon, but I mean, it is doable, and we are placing the tenders for this.
You can sell it after the experiment is finished.
Yeah, this is the plan, to reuse it, to sell to the company. But we are not running the problem of the xenon experiment for dark matter. This is, yeah, I mean, they have a real problem of availability. But in our cases, we are not in this position yet.
Okay, thanks.
You're welcome.
Well, okay, if no other questions, let's start with, let's call André de Gouveia from Northwestern University.